Welcome to the distinguished seminar series, which is dedicated to Professor Cheng Mei, who is with us today in the audience. This is the seminar series of the Department of Civil Environmental Engineering. I'm Lydia Buriba, I'm one of the organizers. And this is the actually inauguration of the series for the spring term. We're going to have 5 talks covering various topics, from fluid mechanics to actually monitoring of infrastructure to other topics. So you can now verify the updates of the program online. The website has changed name. It's a bit easier to remember. It's dss.mit.edu, so you do not need to remember the long URL anymore. And so for today's inaugural talk, we are pleased to welcome Professor Nadine Aubry. So this inaugural talk by Professor Aubry is going to be discussing more of the fluid topics, so from reduced models of turbulence to microfluidics. So let me give you a little bit of background about Professor Aubry. She was named the Dean of the College of Engineering at the Northeastern University in 2012, where she's the university's distinguished professor. She has made research contributions to fluid mechanics, including low-dimensional models of turbulent flows, novel microfluidics methods and devices. Dr. Aubry has received many awards and recognitions for her work, including being elected member of the National Academy of Engineers and the American Academy of Arts and Sciences, and being a fellow of the National Academy of Inventors. Today she'll share some of her work on reduced models and their use in a range of fluid problems, from turbulence to microfluidics. And so without further ado, please join me in welcoming Professor Aubry.
Thank you very much. Good afternoon, everybody. Thank you to Professor Buriba, who invited me, and all the faculty in the department and the students. It's been a pleasure for me to talk to you before the talk. Some of you, at least. It's really a great honor to be here in a speaker series in honor of Professor May. So I'm very honored, and I'll go a little bit through his work, although I'm sure that you all know what he has been doing. Then I thought I would go through turbulence modeling that we did some time ago. And then also from turbulence modeling, I went to microfluidics. I was asked before in meetings before, why is that? So I'll try to explain a little bit how I moved from high Reynolds numbers to very low Reynolds number flows. But basically, under microfluidics, we looked into particle manipulation, particle assembly, as well as mixing. Actually, mixing was the first topic I looked at, coming from turbulence and nonlinear dynamics background. So it's an honor to be here in honor of Professor May. I'm sure that you know better his background. For us in the area of fluid mechanics, we know that he has made breakthrough contributions to this part of fluid mechanics, which has applications to civil, environmental, and coastal engineering, which is kind of different from what I've been doing as a mechanical engineer. But nonetheless, there are, of course, some connections, as fluid mechanics is very fundamental, and some of these problems have fundamentals in common. Professor May is very well known in theoretical hydrodynamics, ocean and coastal wave phenomena, fluid-solid interactions, seabed mechanics, mud flow, mechanics of soil remediation. A lot of waves underlying these problems. So the other thing that we all know in the fluid dynamics community is that he has been very prolific in publishing books. His first book was The Applied Dynamics of Ocean Surface Waves, published by Wiley Interscience as well as World Scientific. Then he published another book on mathematical analysis in engineering, and finally a third book, which is an expansion of his first book on theory and application of ocean surface waves, linear aspects as well as nonlinear aspects. So I studied in France, as some of you may know, and in Grenoble, in the Alps. I did an undergrad degree from National Polytechnic Institute there. And then I also studied the equivalent of another year, but I did it in parallel of my undergraduate degree. And I studied under Emil Hopfinger, that some of you know, especially through our conversations this afternoon. Emil Hopfinger is a well-known person in the fluid mechanics community for work that he did related to a lot of problems in fluid mechanics, but particularly in hydrodynamic instabilities, which is also a common subject with Professor May. So I studied a particular hydrodynamic stability with him back in France. And then I was very intrigued by the next step after hydrodynamic instability, which is really this very random state of turbulence that fluid flow takes mostly as the Reynolds number increases. At that time, so I applied to come to this country. I was very adventurous at the time. I applied to come to this country to study turbulence, and John Lumley at the time was an authority in the field. He was at Cornell, and I went to Cornell to study with him. He was very well known in what is called statistical turbulence, but at the time, there were different thoughts in the field of turbulence. One was statistical turbulence, statistical modeling of turbulence, and he had made a lot of contributions to that field. And at the same time, there was also another thought, which was, well, maybe there should be a more deterministic approach to turbulence. And turbulence, after all, produces all these very random fields for the velocity, the vorticity, the pressure, whatever you look at. And yet, if you look at the fields and what we would call today data analytics or data analysis at the time, you would see what we would call coherent structures. And so when I arrived at Cornell, there was this excitement about these two approaches to turbulence. And then at the same time, there was also a nascent movement to look into the problem from a completely deterministic viewpoint, which would call nonlinear dynamics, dynamical system theory. And so I went to the Department of Theoretical and Applied Mechanics next door and started to talk to Phil Holmes, who was a dynamical system theory person, and started to take his course, actually John Guggenheimer, and he had just published a book, or were publishing a book. Actually, we were one of the first cohorts of students looking at that book, which became very famous on chaos, dynamical system theory, and we're looking for errors in the book. So anyway, that's the story. We looked into turbulence from all these different angles: statical theory, dynamical system theory from the connection with Phil Holmes, but also this coherent structure approach. And the goal was that turbulence is, of course, as we all know, ubiquitous. A lot of people were very interested in solving this big problem. It's one of the remaining unsolved problems in turbulence. And we were going to look at it from a basic understanding, rapid assessment of flows for design. So with, of course, the physics of turbulence from the physics point of view, but also the engineering approach that we wanted to model turbulence for fast assessment of flows for design purposes. So as I said, there were these three approaches. And at the same time, John Lumley himself had introduced what was called at the time, and is still called in the fluid mechanics community, the proper orthogonal decomposition. It was a statistical tool that John Lumley brought to the field of fluid mechanics with the idea of extracting coherent structures from the flow in a rigorous way, in a rigorous fashion. So the question was a mathematical question, which was, we are looking for a function phi, a coherent structure, which you could find in the flow, which would be the most aligned with the velocity. If you wanted to extract a coherent structure from the velocity field, you could do that with other fields as well. But for us, we looked at the coherent structure, which was the most aligned with, in a mathematical sense with the velocity field. And so we looked at the structure that maximizes this ratio of phi projected onto u divided by the square root of phi. If you look at that problem, the phi is actually the solution of this eigenfunction eigenvalue problem, where the kernel, the kernel here is the autocorrelation function, tensor, I should say, ui, uj, ui at x, at a point x in space, uj at x prime, and the phi would be the eigenfunction of this equation, and lambda would be the eigenvalue. Then if you find the phis which maximizing this projection, and it maximizes also, it turns out, the energy, of course, then the velocity field ui, or the velocity component u at the position x, can be expanded in terms of these eigenfunctions with a coefficient an here, such that the coefficients are correlated in such a way that you find the eigenvalue. So Rij can be also decomposed in terms of these eigenfunctions and eigenvalues. And E, the kinetic energy, can be expressed like this. And it turns out that because these functions are orthogonal, it turns out that the energy is now the sum of the various eigenvalues. So, and it turns out that if you do this in a homogeneous direction, which in turbulence is usually the streamwise direction, but as well as the spinewise direction, so x1, x3, typically they're called, that problem reduces to the Fourier transform. But if the velocity field is inhomogeneous in the direction normal to the wall, let's say, for wall-bounded turbulence, then the problem needs to be solved in the, to find the eigenfunctions and eigenvalues of that problem. Lumley had proposed that the decomposition of the velocity field, which is only a four-dimensional velocity in terms of its dependence in three spatial directions and time, would be a four-dimensional decomposition where you would do a Fourier transform in the streamwise direction, a Fourier transform in the spinewise direction, a Fourier transform in time. So these would be, because these were the homogeneous directions, but then you would do a full decomposition with the four eigenvalue eigenfunction problem for the phis in the direction normal to the wall, in the non-homogeneous direction. when I arrived, we thought that perhaps we could keep the direction of time separate so that it would appear in the coefficients of this decomposition, and we would keep the Fourier decomposition in streamwise and spinewise directions, do the proportional decomposition in the inhomogeneous direction perpendicular to the wall. But what to do with these coefficients, which now depends on time? So this time dependency is through the coefficients now, and the idea was to do a Galeckin projection of the Navier-Stokes equations onto these spatial POD modes, and Fourier modes, of course. But then, of course, we had to do a truncation, and so we were betting on the maximization, optimization of the method itself, to think that perhaps with a very harsh truncation, we could still reproduce some of the basic features of the flow. So we did a truncation, which was pretty severe. And then we represented the influence of the higher modes, which had been truncated onto the larger modes through a Heisenberg model. We did this for the wall-bounded turbulence, so we were also limited in terms of the direction perpendicular to the wall and the truncation there. So we had to represent the pressure field at the outer layer. And finally, we did this decomposition of POD/Fourier only for the fluctuation of the velocity, and therefore we had the velocity, the mean flow, which was still there in the equation, and we built a mean flow feedback loop within the model. So the model was actually quite complex, more complex than just severe truncation. So for those of you, and I know some of you are studying the wall region of the turbulent boundary layer, this is a bubble wire visualization of the turbulent boundary layer from a movie taken by Steve Klein at Stanford some time ago in 1967, actually. So this picture of the flow from the top is actually quite famous. And what you see here is that the flow organizing itself in terms of elongated streaks in the direction perpendicular to the wall. I'm sorry, this is not a top flow. The wall is here. And so what the team at Stanford discovered is that there are bursting events. There is this phenomenon of intermittency in time and space corresponding to peaks in the turbulent energy production. And actually, most of the turbulent energy production took place during these so-called bursting events. Our goal was to try to identify these streaks as the coherent structures of the flow, so through this POD decomposition. And in fact, the first mode that we could extract did represent these streamwise counter-rotating walls for the velocity. With the streaks, if you look into the particle materialization lines based on particles emitted in the flow, you can see that in between these counter-rotating vortices, you would see streaks similar to what had been observed by Steve Klein. So that's the first POD mode, of course, with some Fourier modes in the spinewise direction. we actually had 5 spice-wise Fourier modes, and no or only k equals 0 Fourier mode in the streamwise direction, so no variation assumed in this first mode in the streamwise direction. And then, as I said, we tried to reproduce the dynamics of these coherent structures by projecting the Navier-Stokes equations onto this particular mode or coherent structure, and found out that if we were going to keep only 5 spinewise Fourier modes in the spinewise direction and no Fourier modes, or only k equals 0 in the streamwise direction, then the intermittency came up. So if you look at all these modes and their variation in time, you can see that these variables are almost constant, but then at some point they burst, and then they go back to constant value, which is 0 for some of these variables, but non-zero for others, etc. So there is clearly intermittency in that model. When we looked at it from a dynamical system point of view, what we saw was that in phase space, the dynamics, which was almost constant in between the bursts, was corresponded to fixed points, which are represented here in phase space. And as soon as there was a small perturbation, the flow would be thrown away from the fixed point, then that would be a burst. The dynamics would go to the other fixed point, and there would be another perturbation, and the dynamics would go back to the first fixed point. So this was an heteroclinic cycle. At the time, it was not known that heteroclinic cycles could be stable, but clearly we had found a stable heteroclinic cycle, and there was a paper by Guckenheimer and Holmes which proved that actually at the time, which proved that heteroclinic cycles can be stable, which was the case of this particular fluid mechanics example. And in real space, in the physical space, this is a cross-section of our flow. I'm sorry, now here is number 1. And you can see that the flow is two pairs of counter-rotating vortices. It stays there for some time, but then at some point, the dynamics is such that there is a spinewise shift of these vortices. And if you look at the last view compared to the first one, it's the same point, just it's another point in phase space, but in physical space it's just a shifted configuration compared to the first configuration. So clearly intermittency between shifted states of the streamwise walls. If you look at the Reynolds stresses, it was very important to understand this production of turbulent kinetic energy. You could see that the turbulent stresses were spiking during these bursting events. Then later, we looked into the intermediacy in higher dimensional models. We added modes, particularly in the streamwise direction, and we saw that the intermediacy was a little bit different. There was more of an oscillatory space, oscillatory dynamics in between the two fixed points, but basically the intermediacy was robust. And these are some of the streamlines in the flow in the cross-section of the flow. So further works after this was analysis and modeling of many other flows. We looked a lot, my own team looked a lot at the POD and its variance in terms of a decomposition, which is a mathematical tool to look into space-time deterministic dynamics for data analysis. And another very nice feature of this decomposition is that it preserves the symmetry. So if you have some kind of symmetry in the original flow, you are going to find the symmetry in the eigenfunctions, eigenvectors, and the same with scaling properties. So if you assume that your flow has some kind of scaling properties, you are going to find them in the modes, the POD modes. So we wrote quite a bit on this, which means that the oscillations of the modes themselves actually increase as you increase the mode number in the decomposition. So large modes don't have many oscillations, but it's very much like Fourier. But as you increase the n, the order of the mode, then you see many more oscillations. Another type of symmetry is a wave symmetry, which is a space-time symmetry, translation symmetry. If you have it in the original signal, you'll have it also in the decomposition itself. If it's a wave kind of hidden in your flow, you have a wave there, but a lot of other things. You can look at your functions. There is actually a degeneration of the function of the eigenmodes, and you can see that there is a translation symmetry, symmetry of translation in your modes that was, of course, present in your original signal. And then we did also some work on modulated translation symmetry, for modulated waves. So from this work, very focused on dynamical system theory, reduced modeling of turbulence, we got interested in microfluidics. Some of the problems we looked at are manipulation of particles in a bulk flowing using electric field in a small device. So you can see here the dark green is a channel. These are particles. The white parts of this schematic here is the flow. Particles were at first initially randomly distributed in the flow, but after energizing the electrodes at the walls of the walls, then it is possible to attract the particles to the walls. And it is not only possible to attract the particles at the walls, but two kinds of particles could be separated. So here you have one kind of particle which are purple and another kind which are green, and that could be separated. In other configurations, the separation can be a little bit different. For example, here, the interesting feature of this particular configuration is such that some of the particles are being held in the middle of the channel, in the middle of the flow, in a contactless fashion, which could be very relevant if your particles are biological particles and you don't want to take the risk to damage them. And here is another configuration. So this is called Dijkstra Forces. It was being used by, first of all, there were a lot of studies at MIT on this phenomenon a long time ago. Then in the 90s or so, there was a revival of this technique because of its potential for manipulating very small particles. And medical doctors were actually using some of this to separate different kinds of cells, different kinds of bacteria, for example, cancer cells from normal cells. And then from that work, with a lot of applications to biotechnology, medicine, then we looked into manipulation of particles at fluid-fluid interfaces. So now you have two fluids, one on top of the other, with an interface. and you have particles at the interface, trapped at the interface, and you can actually manipulate these particles at an interface so that you can actually form two-dimensional monolayers. And I'll try to go through that work. And finally, fluid mixing. Actually, to tell you the truth, we went from turbulence to fluid mixing because we discovered quite fast that a challenging problem in microfluidics was to induce mixing in these microchannel flows. Of course, when the Reynolds number is very small, there is no mixing. But we could induce mixing by using what is called chaotic advection or other means, but we started by looking into this problem through the chaotic advection point of view, dynamical system point of view, dynamical system theory point of view, which led to some of our successful techniques here. So the first point, the first part of this talk is going to go through particle manipulation in a bulk fluid. My collaborating with Pushpan was saying, and 3 grad students. When you have a particle and you put it in the electric field, there are 2 parts of the force. One is related to what is called electrophoresis, which is the motion of a charged particles in a DC field, where the force is proportional to the charge of the particle and to the electric field itself, and of course in the direction of the electric field, which can be visualized in this fashion. But then the second term is called dihydrophoresis. It's proportional to the dipole moment and the gradient of the electric field, and it corresponds to the motion of a neutral particle. The particle now is not necessarily charged in a non-uniform DC and AC fields. So now you have a low electric field region and a high electric field region, a particle in between, and the particle is going to go from low field region to high field regions along these lines of the gradient of the electric field. So very different from the first approach. If you look at the second approach, the dihydrophoresis itself, and this has been very much studied by now, and expand the dipole moment. So now you have a little particle which is considered as a point dipole, a plus and minus charge. You look at the expression of this dihydrophoretic force, and it's actually proportional to the gradient of the electric field square, where the electric field could be just the electric field if it's uniform, but if it's DC. But if it's AC field and it oscillates, then we consider the root mean square of the electric field. And what is important here is to realize that it's proportional to the volume of the particle, A cubed, but also to the real part of this beta, which is called the Clausius-Mosoldi factor, which depends on, which is the relative polarization of the particle and depends on the complex permittivity of the particle, which itself is a function of the permittivity and conductivity of the particle. But what is important here to realize is that the real part of this Clausius-Mosoldi factor can be either positive or negative. And so that's the basis on which you can actually separate one kind of particle from another kind of particle, because some of the particles are going to go to low electric field regions, while the other kind of particles is going to go to the what did I say, low or high, whatever, the high electric field regions. So that's also a way, as we saw previously, to trap a particle. This is, for example, a cross channel here, and the particle is trapped here in the middle of the channel in a contactless fashion. The particle here is trapped in the region of the electric field which is the lowest. And that I already showed. So we looked at this from a physics point of view, particularly a fluid mechanics point of view, where the electric field is applied, but also fluid mechanics forces enter in the equations here. But of course, in a fluid flow, you usually don't have only one particle. You have a bunch of particles. So we presented them here. Each one is considered as a small dipole. If it's a uniform electric field in between the two walls of the channel, this was actually quite intensely studied by Bonacese and Brady in 1992. The interesting feature here is that the electric field is uniform, but there are particle-particle interactions of electrostatic particle-particle interactions, and in this paper they are actually computed exactly. Now, if the electric field is non-uniform, and we can consider that each particle is so small that it can be considered as a dipole, you have not only the Dijkstra force, but you are going to have also these electrostatic particle-particle interactions in the same fashion as if the electric field was uniform. So, in a real flow here, you can see the walls of the channel here. We have electrodes here. On both sides of the channel. The flow is going from top to bottom. And the particles, this is positive electrophoresis, so the particles are going to regions of high electric fields, and they're going to the corners of these electrodes. But of course, so this is represented here. But because of the particle-particle electrostatic interactions, what you are going to see is also some kind of bridging effect between the two walls. These particles are forming streaks between the walls of the channel. So we wanted to study this phenomenon from a physics first principle approach. So, and from a numerical simulation approach. So the governing equations of our problem are the Navier-Stokes equations for the fluid, and the equations of motions for the particles, where we have the total electrostatic force and torque on the ith particle, if there is a torque, and then the stress tensor on the ith particle surface. So it's a direct numerical simulation approach, type of approach. But in this problem, we consider that the fluid is a perfect dielectric. Actually, I wrote it here. In terms of electrostatic force, as I mentioned, from the physics point of view, we have two components. We have the Hydrophobic dipole force, point dipole force. But we also have the particle-particle dipole-dipole interaction force. So the Hydrophobic force has this expression, as I showed before. And the particle-particle interactions can also be computed exactly through this formula in terms of the electric field. So we use a direct numerical simulation approach from Dan Joseph's groups based on distributed Lagrange multiplier method, where we consider that the domain is both the fluid and the particles, and applied our equations as shown previously. And here is one of the simulations where we put two types of particles for which this beta, Clausius factor, Clausius-Mosody factor is positive, another kind where it's negative, and of course you can see that the particles are going into the parts of the channel where the electric field is either maximum, the highest, or minimum. But you can still see some type of particle-particle interaction. For example, these two particles here were kind of stuck in the middle because they were experiences these very strong interactions between the two particles, and then it took them longer to actually be attracted to the wall. So that's one way to attract particles, but then of course sometimes these particle-particle interactions are so strong that there is what is called the spur chaining phenomenon occurring in the channel, where you see that these particles form these elongated streaks attached to the wall of the channel. And again, the particles are attracted to the electrodes here. We have 4 electrodes in the walls of the channel. But there is also very strong interactions between the particles which form these elongated chains. So we looked into this problem, and in most cases, we wanted to attract the particles as efficiently as possible to the walls of the channels or other areas of the channels, and get rid of these particle-particle interactions. In other physical situations, you want to have interactions, but for actually our applications, we wanted to get rid of these dipole-dipole interactions or particle-particle interactions. So we looked into this non-dimensional parameter, which is basically the ratio between these particle-particle interactions force divided by the Dijkstra force, and see that it behaves like this, proportionally to this beta, the Clausius-Mosotti factor, and also the size of the particle and the distance between the electrodes. And of course, if this non-dimensional parameter is much larger than 1, we have strong particle chaining occurring. If it's about 1, we have both phenomena. And if it's much smaller than 1, particle-particle interactions are negligible, and individual manipulation of particles is possible. And since the Hydrophobic force behaves like beta, and the particle-particle interaction force behaves as beta square, it is possible to actually, as beta goes to 0, it's actually possible to do individual manipulation so that FDP, the Hydrophobic force, is actually larger than the particle-particle interaction force. And this is basically simulating that phenomenon, where here that dimensionless parameter is much larger than 1. We have very strong chaining. It's very difficult to actually grab the particles to any location in the channel because of these very strong particle-particle interactions. But here it's much easier. And of course, if F is smaller than 1, then it's actually easier. And these are some kind of experiments. So this is in AC field. And as we go to what is called the crossover frequency, the frequency for which beta is 0, you can see that the strong chaining becomes much weaker, and yet it's possible to still attract the particles to the walls, to the electrodes. But this approach from a numerical or direct numerical simulation point of view is limited in the sense that it assumes that the particles do not alter the electric field, because this is the point dipole approximation. And so it's only a good approximation if these particles are very small compared to the size of the channel. Now, if your particles become of the same order as the size of the channel, then you have to take into account the deformation of the electric field by the particle itself. And this is a second approach that we developed based on what is called the Maxwell stress tensor, where we have looked into this particular problem that I showed before, where the microfluidic domain here is pretty much square, but with electrodes in the walls of the device. The electric field without any particles can be calculated and shows this electric field contour. contours. The electric potential can be calculated, the boundary conditions, the electric field can be deduced easily. And again, we assume perfect dielectric. The Maxwell stress tensor is a function directly of the electric field itself. And then the Dijkstra force can be calculated by integrating that Maxwell stress tensor over the particle. And if you do this, you see that the ratio between the Dijkstra force calculated from that Maxwell stress tensor divided by the Dijkstra force based on the point-dipole approximation, it should be 1 if we are under the assumptions that the particle is very small. So this ratio is about 1 when the ratio between the radius or diameter of the particle is very small compared to the size of the channel, but it deviates from 1 as the particle becomes larger. So, of course, Dijkstra Forces is an efficient means to manipulate micro and nano-sized particles for holding, bringing to site, and separating particles. But chaining occurs as well, which can be enhanced or avoided. And the point-dipole approximation is valid in most cases, but fails in small devices. So in those cases, you have to base your approach to what we call the Maxwell stress tensor approach. So that's the first part of the talk, and it's kind of needed to understand the second part of the talk, which is directed assembly, basically with the same authors. So some of the physics here, and I was talking to somebody before about the lotus effect, which is being studied in this department as well. So the lotus leaf is hydrophobic. And this is due to the fact that if you look at the leaf under a microscope, you see all these protuberances on the surface of the leaf. This phenomenon is not only used in nature to make hydrophobic surfaces, but also to modify optical properties of surfaces. For example, here, this is a magnified view of the corneal nipple of a moth eye, which has been shown to have superior light absorption property and reduce reflection. So from an engineering point of view, we are interested in designing such or making such surfaces to alter materials' properties, whether those properties are mechanical, thermal, optical. For example, for non-wetting surfaces, as I showed, or to make artificial crystals with some kind of superior optical properties. Our approach to make such surfaces have been bottom-up, meaning that we start with particles and we want to organize them in two-dimensional arrays. And it's scalable, easy to implement, and of low cost. And our approach has been to sprinkle particles at a liquid-liquid interface. It could be a liquid-fluid interface. It could be liquid-liquid or liquid-fluid. Our goal has been to try to obtain a defect-free lattice structure with desirable zero or non-zero and adjustable spacing. And once you do this with your particles at a fluid-liquid interface, you can also solidify the film to make a solid coating, for example, by using UV curable resin as the liquid and curing it by applying UV light. So from a experimental viewpoint, when you sprinkle particles on the surface of a liquid, on the surface of the liquid, you can see the particles getting closer to each other and making this large-scale structure. And what happens is, you see a lot of such sets of particles at first, but these different sets are going to be attracted to one another, and eventually they are attracted to one another and forming only one large-scale structure. And if you look at this phenomenon under a microscope, you see that these particles are actually touching each other, but you also see that there are a lot of defects. And that's because the initial configuration was pretty random, and as the particles get attracted to one another, they block each other, and they form these interstices, these holes between the different particles, which are very non-uniform. This is one of our experiments done with glass particles of radius 12 microns. This one, 40 microns, you see the same defects. So particles self-assemble until touching through this technique. The force is only attractive, but you also have the presence of defects and no long-range order. So this is actually a very well-known phenomenon. It's called capillarity-induced particle attraction. It's used for self-assembly at liquid-fluid interfaces for 2D monolayers. But the drawbacks of this method is that it is not effective on small particles, smaller than 10 microns. The defects, there are a lot of defects and no long-range order. And you can form a close-packed crystalline structure only because the force is only attractive. So non-zero lattice spacing is important for applications, as I showed at the beginning of this section of the talk. So the question is, can we overcome these shortcomings? To answer this question, we have to go back to the physics of this problem. So here you have a spherical particles at an interface, at a free surface. You have a contact angle, surface tension, gamma. This is for a hydrophobic particle, but the reasoning, the argument here works for hydrophobic particles as well. What happens is that the Bond weight is balanced by vertical capillary force in this particular problem. And once you have this balance, then you have also deformation of the interface due to the position of the particle within the interface. And if you have two particles, not only one, then the deformation is different in between the two particles than it is outside the two particles. That creates a net horizontal capillary force arising because of this deformation. And hence the attraction between the particles. So what we have here is the Bond weight balanced by the capillary force, and in dimensionless form, we can rewrite it like this, with B being the Bond number. But for the case of small particles, the Bond number is almost 0. And so there is no vertical capillary force. Therefore, there is no deformation of the interface. Therefore, there is no lateral capillary force. So that means that this capillary-induced self-assembly is not valid on small particles. However, the picture can be completely changed if you impose an electric field on this problem, meaning that now we have the two fluids, the liquid and air, for example, in between two walls in a channel, and we apply an electric field perpendicular to the interface. And you can see that experimentally, we start with the configuration that we obtained using capillarity alone. We apply an electric field, 5,000 volts, and the lattice expands in a very orderly fashion. Then we release the electric field, and we can show that the particles then are attracted to one another, forming a lattice which has long-range order, unlike the initial configuration we started with. And this is another another kind of particles showing the same effect. So that was actually a little puzzling at first, because if you look at electrostatic forces in a uniform electric field, one particle, there is no electrostatic force on a neutral particle in a bulk fluid and a uniform electric field. Then you put two particles, and the dipole-dipole interaction force, or the particle electrostatic particle-particle interaction, even if you go to higher order, is only attractive. How can we build, what is happening in this system which is going to be not only attractive but also repulsive? Obviously, there is a repulsive force as you expand the lattice. So we did some calculation of this problem using the Maxwell stress tensor with two particles at a free surface or at a fluid-liquid interface. And we can see that there is actually a net vertical force in this problem due to the breaking of the symmetry. So what is happening in this part, in the second part of this problem, when in presence of the electric field, is that we now have a vertical electric force, which leads to interface deformation, which then leads to an attractive electric field-induced lateral capillary force. And on top of that, we also have repulsive forces due to dipole-dipole interactions. In this particular problem, this electrostatic force of dipole-dipole particle-particle interactions are actually repulsive rather than attractive. And so we look at the equations again, and now instead of having only the Bond weight and the Bond weight here, with the capillary force, we have an electrostatic force adding to the Bond weight. So even when the Bond weight is 0, very small, as in the case of small particles, we still have a term here in this right-hand side of the equation, which is non-zero, which is going to lead to a non-zero vertical capillary force, which is electrostatic, which is electric field induced, and therefore we can write the vertical force balance in this fashion, where the Bond number is no longer the only non-dimensional parameter in this problem, but we also have a Weber number. And so even if the Bond number is almost 0, then if the Weber number is non-zero, then we have an electric force capillarity, electric force induced capillarity phenomenon. Lateral forces, then we also have the lateral electrostatic force and the lateral capillary force, which here again has two terms, one due to the Bond weight and one due to the electrostatic force. And if we look at the particle distance for large particles, actually our theoretical approach is such that our lattice spacing prediction matches quite well, except for very, very small distances, the experimental results. So conclusion on 2D self-assembly, capillarity-induced self-assembly due to lateral capillary force generated by interfacial deformation. It's not effective on small particles, like nanoscale particles, so you cannot use that for nanotechnology. Presence of lattice defects, no long-range order, and particles touch each other, no control of lattice spacing, and those shortcomings can be addressed by applying an electric field. And I think that I already used too much time, so unfortunately I will not go through the mixing part of the talk. But thank you very much for your patience. I'm sorry that it's so late. Thank you. Very late. Everybody's hungry or tired, and I understand that. Yes.
So one of the most more intriguing things about the poster was the turbulence to microfluidics sort of transition. So when your research was transitioning, was that like piecewise you transitioned the people in your lab to microfluidics, or was it just like an abrupt shift? Like what was that like in terms of like the work that you were performing, and how would like
Yeah, actually, an answer to that question is actually through mixing, because we did the mixing before the particle manipulation. So, and what happened with the mixing part of the of our research is that we wanted to put a sample with a reagent. We wanted to induce mixing, obviously, and so we designed a technique which actually, I can explain what physically we did, but if you look at the material lines, particle lines in this flow, you can see stretching and folding, and so this is called chaotic advection. So that was really the connection between the dynamical systems approach to turbulence and, oh, there is a big problem here for microfluidics that perhaps we can contribute with our dynamical systems theory approach. And it became clear, you know, that we had actually a center at the time. And somebody from industry, we were having all these workshops with industry, and somebody from industry said, asked me the question whether I knew how to induce mixing in a small channel. And so we started to work on this. So actually, the morale of this, I think, is that it looks like it's not connected, but because we were already very interdisciplinary in the first problem between turbulence and numerical system theory, we had two sets of tools in our pocket. And then the other moral of the story, I think, is when you talk to people from, in kind of your field, but which would perhaps bring a question from industry, which would be really crucial for the applications, then I think that could be very powerful. So I think the interdisciplinarity is very important, especially nowadays. You know, a lot of the problems are interdisciplinary because, you know, the classic problems in fluid mechanics or in other fields have been solved already. But at the boundary between different fields, systems are more complex, but also have not been solved necessarily. And then I think also talking to people from the application side, you know, from industry or national labs, can be also very useful.
Regarding the bursting, but it looks like when you have a turbulent bursting, your Venus stress goes like positive and negative. Does that mean the bursting doesn't contribute to the timing average Venus stress, but only contribute to the turbulence energy production?
The production of the bursting?
Yeah. Does it contribute to the timing average Venus stress? Because it goes fluctuating when you have a burst.
So I'm not sure. I think I missed some part of your question, but from a dynamical system point of view, the bursting is actually triggered by a perturbation. And for us, the perturbation in the numerical simulation or this system, even the model, was brought by the pressure in the outer layer. So that was the perturbation in our system. And so the size of the perturbation, is important, obviously. Of course, there were other perturbations of smaller magnitude, but the main perturbation came from the pressure at the outer wall, at the outer layer.
You have to think of the Venus stress fluctuating.
Yeah, so the Reynolds stress, of course, is a direct consequence of the fluctuation of the velocity.
But the bursting contributes to the average Venus stress.
Right. Yes, it's actually the most contribution. Yeah, we were talking about this. I forgot exactly how much, but probably more than 70%, perhaps 80%.
Any other questions?
I'm not familiar with the POD at all. Can you explain roughly just what is the role of POD in both your problem? One is the turbulence, one is the microfluidics.
Yeah, so.
Does it play?
No, actually, I didn't show the application of POD in microfluidics.
Ah, okay.
Yeah, the transition there to answer the previous question was more the dynamical systems approach, right? Dynamical system theory approach. So POD is a data analysis tool, right? You have this completely random field, a turbulent field, right? It's before actually this kind of approach. There are also a few other approaches called coherent structure approaches. People did not know how to extract what is called coherent structure, some kind of organized feature in these seemingly random velocity vorticity fields. So this is a rigorous mathematical approach to extract coherent structures or features in the flow.
So the method depends on the data. Now,
yes, it's based on data.
Suppose the phenomena has multiple scales, many types, vastly different time scales. How much data do you need in order to apply this method?
Yeah, if you want to extract only information at a certain scale, you need the data at that scale. Now, if there are larger scale phenomena and you are here, but yet the phenomena has this scale, you are going to miss that scale, right? Or you are going to capture only a portion that you are not going to understand that this is a large scale effect. So there is no miracle in the sense that you do need to have data to extract the features that you want, that of the length scale, time scale that you want to extract from.
Building a little bit on this last question, I'm familiar with this approach, particularly for the 2D turbulence, where you have, for example, these very large structures are very well defined. Let's say you have inverse cascades with the emergence of these vortices that start dominating. And at the time where it was really much applied, there was very low power in terms of computation and data analysis. So in light of all the sort of very passionate discussions of big data and machine learning.
Right, yes.
So how is there a resurrection of the dynamical systems approach in light of the algorithm that are searching for these features extractions in this domain at this time? Or are we moving away from the dynamical systems approach altogether and just extracting features without relating them to the equations of motions altogether?
Yeah, so it's a good question. Yeah, it's definitely a data analysis tool, which can be very useful, right? From big data, looking very disorganized, you want to extract something which makes sense. So this was basically the problem we had in turbulence 30 years ago, right? But now you have it in all fields, right? Because data are being collected when you talk on your cell phone and these kind of things. So it is a data analysis tool, and I think that some of the techniques, actually somebody even wrote a book recently on using these kind of techniques for big data, for data analytics. So that's one thing. But then we did quite a bit of studies on this actually. Just the POD as a data analysis tool. And actually, we took it to space-time data analysis later on. So you have, space and time, how can you extract data which makes sense? But then we also took it to the point where we wanted to understand some dynamics, and I think the meteorologists are also doing this with, atmospheric data, weather data, trying to reproduce and predict actually what is going to happen in the future based on data that you have today. You know, so I do think that the big data people are one of the approaches is based on these kind of tools, but only the data analysis part of it.
Not the connection with the actual dynamics and that govern these structures. After you detect these structures, then how are they actually affected via the equations of motion?
Yes, the only thing that I would say is that, yes, the first approach was to look at coherent structure in space. But the technique can also be used to look at data in space and time. So now you have f of x and t, which you look at the data, they look very random. What do you do with them? Well, this decomposition is actually very good at looking at space-time kind of coherent structures, organized features in space and time. We wrote quite a bit on this. The expansion of this decomposition, which was basically a statistical tool at first, it's also actually very good for a space-time completely deterministic tool.
Yeah, I mean, what I'm really interested in is that connection with then the actual stability of these structures and how the equations of motion. So once you detect these structures, how could you reduce your dynamical system model to actually understand their stability, their features? So I can see how.
So that's, yes, that's the part of the talk I already talked about. Then we did quite a bit of work also on the data analysis tool to extract space-time features, which was your second question. Yeah, that's a good question.
All right. Any other questions? No? All right, Julie, thank you, our speaker.
Thank you so much.